So for our next example, determine if this function g of x, y, given by this piecewise function, is continuous at the point 0, 0. If not, classify the type of discontinuity. So since this is a piecewise function, well, we can just determine the limit, okay, of this function here, okay, as the point x comma y goes to 0, 0, and show that this is equal to the other definition of the function here, okay? So, let's see. To do that, let us have y equals k times x cubed, where k is some number. Then, we have here the limit of g of x comma y as x comma y goes to 0, 0. Okay? This will be equal to the limit. Since we are just approaching the point 0, 0, we are going to use this definition of the function. So we will have here x cubed y over 2x to the 6 plus y squared as the point x comma y goes to 0, 0. And if we are passing along this curve or we are moving along this curve here, then this expression here can be transformed into the following. So the limit here becomes, we have x going to 0. And then we will have x cubed times k x cubed divided by, we have 2x to the 6 plus we have kx cubed squared. And then if we simplify this, we will have the limit x goes to 0. We have kx to the 6 over 2x to the 6 plus k squared, k squared x to the 6. Okay? And then we'll have limit as x goes to 0 of k over, so if we simplify this, this will just be k over 2 plus k squared. Okay? Or simply, we have k over 2 plus k squared. So notice for different values of k, the limit will also be different. Okay? So if k equals 0, the limit of g of x, y, as x, y goes to 0, 0, this will be equal to 0. If, say, k equals 1, then the limit as x, comma y goes to 0, 0 of the function g of xy, this will be equal to 1 over 3. So different limits, therefore, the limit does not exist. Therefore, limit of g of x, comma y, as the point xy goes to 0, 0 does not exist. So the discontinuity is essential. So the function is discontinuous and the discontinuity is essential. Okay? Or so g of x comma y has an essential discontinuity at the point 0, 0. Okay? So for our last example, determine if this function h of x given by this piecewise function is continuous at the point 0, 1. If not, classify the type of discontinuity. So at the point 0, 1, and it's actually part of this curve here, y squared minus x squared equals 1. Okay? And therefore, at this point 0, 1, there's different definition. Okay? So at the point 0, 1, the function is 2. Otherwise, this is the function. Okay? Or otherwise, such that this equation here is true, this will be the definition of the function. Okay? So, for this, let's see. Let's start with the following. Say, consider the curve or the line along x equals 0. Okay? Then, what will we get? The limit of h of x comma y as the point x comma y goes to 0, 1. This will just become the limit as y goes to 1. Y goes to 1 of h comma y. Okay? Again, still, we are assuming that we are not on this. Okay? We are not on this lines. So, or curves. So, we'll just have y minus 1 quantity squared over sine inverse of minus y squared plus 1. And notice this is what? This is just 0 over 0. Y equals 1, numerator is 0. Denominator will have sine inverse of 0, which is still 0. So we can apply here L'Hopital's rule. So we will now have limit. Y approaches 1. In the numerator, we'll just have 2 times y minus 1. On the denominator, check that this is just negative 2y divided by square root of 1 minus negative y squared plus 1 quantity squared. So hope you still remember the derivative of sine inverse. And if we simply manipulate this or look at this. As y goes to 1, this guy here, it's non-zero. Numerator here, it's non-zero. And this guy here, it is also non-zero. Therefore, this guy here, it's non-zero. So as y goes to 1, this will be equal to 0. Okay? So that's along x equals 0. Now let's consider the line y equals 1. Y equals 1. So we move along the line y equals 1. We have here limit as the point xy goes to 0, 1 of h of xy. We'll just have the limit as x goes to 0. The numerator will just have x squared. For the denominator, since y equals 1, this guy here will be equal to 0. So this guy here will be equal to 0. So the denominator, it's just sine inverse of x squared. Okay? So as x goes to 0, we'll have 0 over 0 in here. And therefore, we can apply L'Hopital's rule. So this is now the limit as x goes to 0 of 2x in the numerator. In the denominator, again, just check. This is 2x over square root of 1 minus x to the 4. Okay? And if you simplify this is simply the limit as x goes to 0 of square root of 1 minus x to the 4. And as x goes to 0, this is equal to 1. And notice that this guy here, they are not equal. So limit does not exist. So limit x comma y goes to 0 comma 1 of h of xy does not exist. So h of x comma y has an essential discontinuity. Discontinuity at 0 comma 1.